Now see, determining the resistivity of the material of a given wire using meter bridge. See, this meter bridge is actually the application of Wheatstone's bridge. Okay, now let's see the first question. Which of the following statement is true regarding null points in finding the resistance of unknown wire using meter bridge? At null point, current through the galvanometer is 0. That's true. At null point, condition is balanced Wheatstone's bridge. That's also true. Deflection of galvanometer in the same direction on either side of null point. That's false. So statement 1 and 2. 1 and 2 means this one. Okay. Now let's see. Wheatstone's bridge is an arrangement of resistors used for accurate measurement of. See, Wheatstone's bridge is an arrangement of how many resistors? 4 resistors. Okay. So this one. Next, the resistivity of the material depends on the material only. Okay. And we can say it depends on temperature also. But here it is given that length of the wire, resistivity is independent of the length or diameter or density of the wire. It depends on the material of the wire. Okay. Now a thin uniform wire AB of length 1 meter, an unknown resistance X and a resistance of 12 ohm are connected by thick conducting strips as shown. A battery and a galvanometer are also available. In the following diagram, connections are given to measure the unknown resistance X using the principle of Wheatstone's bridge, the appropriate connections. Actually, as this is a metal strip, these 2 points are identical. Means A and D are electrically identical. Okay, and see, so the cell is to be connected across the resistance wire, or cell is to be connected across B and A, or we can say it is to be connected across B and D. Cell across B and D, then the galvanometer should be connected across E and C. Okay, battery across B and D, galvanometer across E and C. Okay, battery across B and D and galvanometer across E and C. Okay, this one. Right? Battery is to be connected across the uniform resistance wire. Okay, this is the resistance wire. So the battery is to be connected across B and A, but A is electrically identical to D. So the battery is to be connected across B and D. So if the battery is connected like this, right, then the galvanometer should be connected across these 2 points. Okay, right. Now let's see what we have next. A meter bridge experiment. A thin uniform wire AB of length 1 meter and unknown resistance X and a resistance of 12 ohm are connected. In the above question, after appropriate connections are made, it's found that no deflection takes place in the galvanometer where the sliding jockey touches the wire at a distance of 60 cm from capital A. What's the value of resistance X? What's the value of resistance X? Okay, now here we have, see, this is 60 cm, so this will be 40 cm because the total length of the wire is 100 cm. That's why it's being called as meter bridge. Okay, so X divided by 12, that must be equal to 60 by 40, or it is 3 by 2. So we will get X equal to 18 ohms. X equal to 18 ohms. This one. Now for the electrical circuit shown in figure, the potential difference across the resistor of 400 ohm as will be measured by the voltmeter V of resistance 400 is. See, this is actually Wheatstone's bridge, and here we have 400 ohm resistance that is connected in parallel with a voltmeter of resistance 400 ohm. So the effective resistance of this combination will be 200, because when two identical resistors are connected in parallel, effective resistance will be half of the resistance. So here it will be 200. So we have this 100 and 200 connected in series. Total we have 10 volt. So this 10 volt will be divided in direct proportion to their resistances. So see, the resistances are 100 and 200, or they are in the ratio 1:2. So the total voltage 10 will be divided in the ratio 1:2, means we have to divide 10 to 1 plus 2, 3 equal parts. So each part will be 10 by 3. Okay, 10 by 3, 10 by 3, 10 by 3, 3 parts. The voltage across this will be one part and the voltage across this will be two parts. So 10 by 3 into 2. That is the voltage across this branch, that is 20 by 3. That will be the reading of the voltmeter. Okay, so 20 by 3 volts. Now in a simple meter bridge circuit, the gaps are bridged by coils P and Q. A balance point obtained when the jockey makes contact at point 40 centimeter from the NP. Okay, on shunting the coil with a resistance of 50 ohm, the balance point is moved through 10 centimeter. See, on shunting the coil Q with a resistance 50 ohm means the effective resistance across that gap will decrease. Okay, so this 10 centimeter will be towards right, or the balance point will be 50 centimeter when Q is shunted with 50 ohm resistance. Balance point 50 centimeter means the effective resistance across the two gaps will be equal, or the resistance P will be equal to the parallel combination of Q and 50 ohm. Okay, so first P by Q, that is balance point is 40, and L by 100 minus L will become 40 by 100 minus 40 is 60, so it is 2 by 3. Now when Q is shunted with a resistance of 50 ohm, balance point shifts to 50 centimeter. Means P will be equal to the parallel combination of 50 and Q. Okay, so this is the parallel combination of 50 and Q, that is exactly equal to P. So we will, from here we will get P by Q equal to 50 by 50 plus Q. Okay, and P by Q we already have 2 by 3. So 50 by 50 plus Q equal to 2 by 3. Or this can be written as see 50 by 50 plus Q equal to 2 divided by 2 plus 1. So this 50 corresponds to 2. Okay, so this 50 also corresponds to 2. Okay, then see if 2 is 50, then this 1 corresponds to Q. Okay, so this factor is half of this one. So this factor Q will be half of this, means it is 25. So Q will be equal to 25. See, when Q equal to 25, P will be 25 into 2 by 3, that is 50 by 3. So P is 50 by 3 and Q is 50 by 2, that is 25. 50 by 3 and 50 by 2 ohm respectively. Now what's the resistance of an open key? Resistance of an open key is infinite. Okay. Now resistance in the two gaps of a meter bridge are 10 and 30 ohms respectively. If the resistances are interchanged, the balance point will shift by. Now see, 10 by 3 equals L1 by 100 minus L1, that is 20. See, this should be in the ratio 1:3. So it must be 25 and 75. Total length is 100 centimeter, that is to be divided in the ratio 1:3. Okay, now if the resistances are interchanged, it will become, see, 75 and 25. See, in the first case, the balance point is 25, and in the second case, the balance point will be 75. Or we can say the balance point shifts by 50 centimeter. This one. Okay. Now, in the shown arrangement of the experiment of a meter bridge, if AC equals corresponding to null deflection of galvanometer X, then what would be its value if the radius of the wire AB is doubled? Now see, it depends only on the ratio of this L and 100 minus L. Or if the wire is uniform, that balance length is independent of the cross-sectional radius or cross-sectional area. Okay, depends only on length. Now, so it will be X only, right? Now, an unknown resistance R1 is connected in series with a resistance of 10 ohm. This combination is connected to one gap of a meter bridge, while resistance R2 is connected in the other gap. The balance point is 50 centimeter, means the resistances in the two gaps are equal. See, in one gap the resistance is 10 in series with R1, means 10 plus R1, and the resistance in the other gap is R2. Okay, now when 10 ohm resistance is removed, the balance point shifts to 40 centimeter. See, when 10 ohm resistance is removed, then ratio will be R1 by R2 and it is equal to 40 by 60, means it is 2 by 3. See, here we will get R2 minus R1 equal to 10 ohm, and here we have R1 by R2, that is 2 by 3. So R1 equal to 20 ohm and R2 equal to 30 ohm. Okay, R1 equal to 20 ohm, R2 equal to 30 ohm. So we have to find the value of R1. Right. The resistance in the two arms of meter bridge are 5 ohm and R ohm. Okay. When the resistance R is shunted with an equal resistance, the new balance point is at 1.6 L1. The resistance capital R is. Initially, see, when there is 5 ohm in the left gap and R ohm in the right gap, balance point is L1. So 5 by R equal to L1 divided by 100 minus L1. Now R is shunted with an equal resistance, means it will become R by 2. So 5 divided by R by 2, that is equal to 1.6 L1 divided by 100 minus 1.6 L1. Okay, now see, this 2 will go to the numerator. So on the left side there will be 2 into 5 by R. 2 into 5 by R. That 5 by R can be replaced by L1 by 100 minus L1. So 2 into L1 by 100 minus L1, that is equal to 1.6 L1 divided by 100 minus 1.6 L1. Okay, now this 2 and 1.6 can be, see, both can be divided by 0.4. So this 2 by 0.4 will be 5, 1.6 by 0.4 will be 4. Okay, so here we will have 5 and here we will have 4. Okay, this L1 and this L1 can be cancelled. So on the left side we will have 5 into 100 minus 1.6 L1, and on the right side we will have 4 into 100 minus L1. Okay, now this is 5 into 100, here we have 4 into 100. When this 4 into 100 is taken to the left side, it is minus 400. So 500 minus 400, that is 100. Then 5 into 1.6, that is 8 L1, and here we have 4 L1. Okay, so when this minus 8 L1 is taken to the right, it will be plus 8 L1 minus 4 L1, that is 4 L1. Now here we have L1 equal to 25 centimeter. So if you put this 25 divided by 100 minus 25 means 75. 25 by 75, that is 1 by 3. Okay, so 5 divided by R is 25 by 75, or we can say this is 1 over 3. Okay, so R will be 15 ohm. Okay, R equal to 15 ohm. Now let's see, the meter bridge shown is in balanced position, P by Q equal to L1 over L2. If we know interchange the positions of the galvanometer and cell, the bridge, will the bridge work? Definitely. Okay, what will be the balance condition? Same as before. Okay, positions of this cell and galvanometer can be interchanged without any other change, without disturbing the balance condition. So this must be the correct choice. Okay, in a meter bridge setup, which of the following should be the properties of the 1 meter long wire? High resistivity and low TCR, high resistivity and low temperature coefficient of resistance. Okay, now in a meter bridge experiment, we try to obtain null point at the middle. This reduces systematic error as well as random error. Okay, systematic error as well as random error. See, the null point must be close to the center of the meter bridge wire. Okay, a student obtained following observation in an experiment of meter bridge to find unknown resistance. The most accurate value will be the one that is closest to the center of the wire. Okay, which one? That is this one, because here the balance length are 52 and 48. Those two values are the values which are closest to the center of the wire. Okay, now let's see, in a meter bridge experiment, null point is obtained at 20 centimeter from one end of the wire when resistance X is balanced against another resistance Y. Okay, now if X less than Y, then where will be the new position of the null point from the same end if one decide to balance a resistance of 4x against y? Now see, x by y will be equal to 20 by 100 minus 20, that is 80. Okay, now 4x by y, that will be equal to 8 L divided by 100 minus L. Now this x by y can be written as, that is 1 by 4, or this x by y can be replaced by 1 by 4. So here we will get 1, or L and 100 minus L are equal, or L will be equal to 50 centimeter. Okay, L equal to 50 centimeter, new balance length. A meter bridge is set up as shown to determine an unknown resistance X using a standard 10 ohm resistor. Galvanometer shows null point when tapping is at 52 centimeter. Okay, so this is 52 and this is 48. Okay, 48. Now the n corrections are 1 centimeter and 2 centimeter respectively at the ends A and B. See, this is A and this is B. Here the n correction is 1 centimeter, so the actual length is 53. Here the n correction is 2 centimeter, so the actual will be 50. 48 plus 2, 50. Okay, now see, x divided by 10, that will be equal to 53 divided by 50. Okay, 52 plus 1 and 48 plus 2, because the n corrections are 1 and 2. So we will get x by 53 equal to 10 by 50. So x will be 53 by 50 into 10. Or this can be written as 106 by hundreds. Okay, so it will be 10.6 ohms. 10.6 ohms. Now the determination of a resistance of a given wire by using Ohm's law. See, the point to be kept in mind for verification of Ohm's law: ammeter and voltmeter should be connected in series. That's wrong. Ammeter should be connected in series and voltmeter in parallel. That is the correct option. Now let's see what we have next. From the given VI graph for three resistors R1, R2 and R3, it may be concluded that, see here, the slope of the graph will give you delta Y divided by delta X. Means quantity along the y-axis by quantity along the x-axis. Here we have voltage along y-axis and current along the x-axis. So the slope of the graph will give you the resistance. And see, slope of this one is more than the slope of R1. Okay, and slope of R3 is more than the slope of R2. Okay, slope is more, resistance is more. So R1 less than R2 less than R3. So this must be the correct option. Now in an electric circuit, current becomes half when resistance is doubled, because current equals V divided by resistance. Okay, so current will become half when resistance is doubled. Choose the correct statement regarding Ohm's law. It's valid for any circumstances that it is independent of temperature. That's a wrong statement. Ohm's law is valid for all conducting materials. That's also wrong. Temperature must be constant for validation of this Ohm's law. That's true. Now the potential difference between the terminals of an electric heater is 60 volt when it draws a current of 4 ampere. Okay, what current will be the heater draw if the potential difference is changed to 127.5 volt? Okay, now the resistance must be the same. Okay, see, when 60 volt is connected, the current is 4 ampere. So 60 by 4 is the resistance. When 127.5 volt is connected, if the current is I, then 127.5 by I is the resistance in the first case. And this is the, see, these two must be the same. Okay, so we will get I equal to 8.5 ampere. Okay. Now let's see IV graph. Here current is along the y-axis and voltage along the x-axis. So slope will give you the conductance. So conductance of Q, slope of Q is more. So conductance of Q is more, or the resistance of Q is less, or the resistance of P is more. Okay, so RP greater than RQ, right? Now the current voltage graph of ohmic devices must be linear. Okay, linear. Okay, means it must be a straight line, that is linear. An ammeter is connected in series with the circuit. Next, the SI unit of electrical conductance is Siemens. This one. Now, A wire of uniform cross-section capital A, length L and resistance R is bent into a complete circle. The resistance between any two of diametrically opposite points will be. See, the total resistance is R. When it is divided into two equal segments, see the resistance of each part, okay, the resistance of the part above the terminals and below the terminals will be equal. Each will be equal to R by 2 and effective resistance will be R by 4. Okay, this one R by 4. Now the electric resistance of a certain wire of iron is capital R if its length and radius both are doubled. Okay, see, this is the expression for the resistance. When length is doubled, resistance will become twice. Okay, when radius is doubled, the resistance will become 1/4. Okay, so altogether the resistance will become half. Okay, so the resistance will become halved. Resistance will be halved, and specific resistance being a property of the material, it will remain unchanged. Resistance will become halved and the specific resistance will remain unchanged. This must be the correct option. When a piece of aluminum wire of length, finite length is drawn to reduce its diameter to half its original value, the resistance will become. See, when a uniform cylindrical wire is stretched uniformly so that the radius becomes 1 by n, then the resistance will become n raised to 4 times. Here it is stretched uniformly so that the radius becomes half. Means 1 by n, what stands here? It is 1 by 2. So n equal to 2 and the resistance will become n raised to 4 times. Okay, means 2 raised to 4 times or 16R. Okay, 16R means 16 times. Okay, and how do we get this one? R dash equal to n raised to 4R. See, this is the expression for the resistance, rho L divided by pi R square. Now multiply both the numerator and denominator by pi R square. So in the numerator there is L into pi R square, that is length into cross-sectional area, that is volume. And in the denominator we will have pi square R raised to 4. When a wire is stretched uniformly, resistivity won't change, total volume will not change, pi square will not change. So we can say resistance is proportional to 1 by R raised to 4. So R dash by R equal to R by R dash whole raised to 4. And it's given that R dash is R by N. So R by N, that will be N raised to 4. Okay. Now, as the temperature of a metallic resistor is increased, the product of resistivity and conductivity. See, conductivity is the reciprocal of resistivity. So the product of resistivity and conductivity is 1, or it is a constant. And it is independent of temperature. Okay, it remains constant, that product. If the length of a given cylindrical wire is increased by 100%, see, original length is 100%, original resistance is 100%. So 100% length is 1L, 200% is 2L, 150% is 1.5L, 80% is 0.8L, like that. Okay, means percentage can be converted as fraction by dividing with 100. Fraction can be converted as percentage by multiplying with 100. Now see, we have length 100%, now it is increased by 100%, means it becomes 200%. Or a wire is stretched uniformly so that length becomes twice. Okay, means it is increased by 100%. See, this is the expression for resistance. If you multiply both the numerator and denominator by L, we will get a rho L square by AL. Okay, AL, cross-sectional area into length, that is the volume. When a wire is stretched uniformly, volume will remain unchanged, resistivity won't change. So we can say R proportional to L square. So R dash by R will be L dash by L whole square. L dash is twice the original length. So we will get 4. So R dash is equal to 4R. Originally it was 1R and it is 100%. Now it is 4R, means it is 400%. So it is increased by 300%. Okay, the change in resistance of the wire will be 300%. The current voltage graph for a given metallic conductor at two different temperatures are T1 and T2 are shown in figure. See, this is a current versus voltage graph and the slope will represent conductance. So conductance at T1 is more, so resistance at T1 will be less. So that T1 temperature is smaller than T2. Okay, T1 smaller than T2, this one. Alright. Now in the measurement of resistance of a wire using Ohm's law, the plot between voltage and current is drawn as shown. The resistance of the wire is. Here the resistance of the wire is slope of this voltage current graph. Okay, this is a line inclined equally to the x and y axis, or the angle made by the straight line with the x axis is 45, and the slope of this graph will give you the resistance. Slope is tan theta, or it is tan 45, and it is equal to 1 ohm. Okay, so this must be the resistance. Now resistance and figure of merit of a galvanometer by half deflection methods. Now see the first question, the instrument that is used for detecting electric current, that is galvanometer. It is used to detect the current rather than measure current, because it shows a large deflection even for a small current. Okay, see in half deflection method, a high resistance box is connected in series with the battery so that the deflection of the galvanometer is brought within the scale. Okay, that's true. Okay. Next, while performing the galvanometer experiment using half deflection method, a student got almost the same value for S. Every time, whatever be the value of capital R he had set in the resistance box. This is because the resistance box in which S is put is faulty. Resistance G is very low. In half deflection method, current gets divided between G and S, and R is very high. That is the right option. A moving coil galvanometer has 150 equal divisions. Its current sensitivity is 10 divisions per milliampere. See, 10 divisions are equivalent to 1 milliampere. So 150 divisions will be equivalent to 15 milliampere. So the full scale deflection current for the given galvanometer is 15 milliampere. Okay, Ig. Now voltage sensitivity is 2 divisions per millivolt, and there are 150 equal divisions. So the full scale deflection voltage is 75 millivolt. Vg equal to 75 millivolt. Okay, now the galvanometer resistance will be, full scale deflection voltage divided by full scale deflection current, that we will get 5 ohm. That is the galvanometer resistance. Now it is to be converted into a voltmeter. See, in order that each division reads 1 volt. Each division reads 1 volt. So 150 divisions are there. So the full scale deflection voltage is to be increased to 150 volt. Okay. So we have to convert it into a voltmeter capable of measuring a maximum voltage of 150 volt. Okay, now the full scale deflection voltage is 75 millivolt. That is to be converted into a voltmeter to measure a maximum voltage of 150 volt. Okay, so the factor by which its voltage capacity is to be increased, small n equal to V by Vg. That is equal to 150 divided by 75 into 10 raised to minus 3, that is 2000. So its voltage capacity is to be increased by 2000 times. So we have to connect a high resistance called a multiplier in series with the galvanometer. Okay, and that multiplier value X is equal to N minus 1 into G. Means 2000 minus 1 into G is 5. See, 2000 into 5 is 10,000. 10,000 minus 5, that is 9,995. Okay, this is to be connected in series. A galvanometer of resistance 200 ohm gives full scale deflection for a current of 10 raised to minus 3 ampere. To convert it into an ammeter capable of measuring up to 1 ampere. Okay. So the factor by which its current capacity is to be increased. N is given by I by Ig, where Ig is the full scale deflection current of the galvanometer, and capital I is the ammeter, the maximum current capacity of the ammeter to which it is to be converted. Okay, so that we will get thousands. Then the small resistance called shunt to be connected in parallel with the galvanometer, that is capital G divided by N minus 1. galvanometer resistance divided by n minus 1. So 200 divided by 1000 minus 1. You can take it approximately 200 divided by thousands. That is 0.2, or we can express it as 2 into 10 raised to minus 1 ohm. Okay. A galvanometer with a resistance 100 ohm is converted into an ammeter with a shunt of 0.1 ohm. The galvanometer shows full scale deflection for a current of 100 microampere. Okay. Then what will be the minimum current in the circuit for full scale deflection of galvanometer? See, shunt is capital G divided by n minus 1, where n is the factor by which its full scale deflection current is increased. Okay, so n minus 1 will be G by S. Shunt is given as 0.1 and G is equal to 100, so n minus 1 will be 1000 and n will be equal to 1001. So I, full scale deflection current of the ammeter, that is n into Ig, so 1001 into 100 microampere. See, microampere is actually 10 raised to minus 3 milliampere. Okay, so this will be 100.1 milliampere. Okay, 100.1 milliampere, this one, right? The range of a galvanometer of resistance capital G, ohm is V volt, the resistance required to be connected in series with it in order to convert it into voltmeter of range n times V. Okay, that is x equal to n minus 1 into G, x equal to n minus 1 into G, this one. Okay, now the scale of a galvanometer of resistance 100 ohm contains 25 divisions. It gives a deflection of 1 division on passing a current of 4 into 10 raised minus 4 ampere. So the full scale deflection current will be 4 into 25, 100 into 10 raised minus 4, that is 0.01 ampere. Okay, that is the full scale deflection current. And full scale deflection voltage will be G into Ig. And galvanometer resistance is given as 100 ohm and Ig we have 0.01 ampere. So the full scale deflection voltage is 1 volt. Now it is to be converted into a voltmeter capable of measuring a maximum voltage of 2.5 volt. Okay, so the factor by which its voltage capacity is to be increased. N equal to V by Vg. That is equal to 2.5 by 1, that is 2.5. So the high resistance that is to be connected in series, it's called a multiplier and its value x equal to n minus 1 into G, 2.5 minus 1 into 100, that is 150. Okay, 150 ohms, this one. A galvanometer of resistance 200 ohm gives full scale deflection with 15 milliampere current in order to convert it into 15 volt range voltmeter. See, galvanometer resistance is 200 ohm and full scale deflection current is 15 milliampere. So the full scale deflection voltage Vg, that is capital G into Ig, that is 200 into Ig is 15 milliampere, means 15 into 10 raised minus 3, that we will get 3 volt. Now it is to be converted into a voltmeter to measure a maximum voltage of 5 volt. So the factor by which its voltage capacity is to be increased, V by Vg, that is 15 over 3, that is equal to 5. So the high resistance called multiplier to be connected in series, x equals n minus 1 into G, that is 5 minus 1 into 200, that is 800 ohms, this one. Okay. Now a galvanometer having a resistance of 50 ohm gives a full scale deflection for a current of 0.05 ampere. Okay, the length in meter of a resistance wire of area of cross section 2.97 into 10 raised minus 2 centimeter square, that can be used to convert the galvanometer into an ammeter which can read a maximum of 5 ampere current is. See, now the maximum current that the galvanometer can read is 0.05 ampere. It is to be converted into an ammeter capable of measuring 5 ampere. So the factor by which its current capacity is to be increased, N equals I over Ig, that is equal to 100. So the small resistance called shunt to be connected in parallel with the galvanometer, that is capital G over N minus 1. So this capital G galvanometer resistance is given as 50 ohm. So 50 divided by 99. Okay, now we have to get the length of a resistance wire that is to be connected in parallel with the galvanometer. Okay, see, resistance is given by rho L divided by capital A, where L is the length and capital A is the cross-sectional area. Capital R is the shunt that is to be connected. So we can see if we replace this R resistance with the shunt S. So SA by rho, that is the length of the required wire. Okay, shunt resistance is 50 divided by 99. Then cross-sectional area is 2.97 into 10 raised minus 2 centimeter square can be converted into meter square by multiplying with the 10 raised to minus 4. And in the denominator we have the resistivity, and it is given as C5 into 10 raised to minus 7 ohm meter. Okay, now see, let's first consider the power. Okay, now see 10 raised to minus 2 and 10 raised to minus 4. 10 raised to minus 2 and 10 raised to minus 4, that is 10 raised to minus 6. 10 raised to minus 6 and 10 raised to minus 7, that is 10 raised to minus 1 in the denominator. Okay, when it is taken to the numerator, it will be 10 raised to plus 1. Okay, then 50 divided by 5, that is another 10 here. 10 into 10 raised to plus 1 means 100 into 2.97, that is 297, and in the denominator we have 99. 297 divided by 99 is exactly 3. Okay, so we will require a wire of length 3 meter. Okay, next, an ammeter of range 5 ampere is to be converted into a voltmeter of range 10 volt. If the resistance of ammeter is 0.1 ohm, then what resistance should be connected in series? See, full scale deflection voltage Vg is given by capital G, that is 0.5 volt. It is to be converted into a voltmeter capable of measuring a maximum voltage of 10 volt. So the factor by which its voltage capacity is to be increased, N equals V over Vg, that is equal to 10 over 0.5, that is 20. So the high resistance called multiplier that is to be connected in series with the galvanometer so as to convert it into a voltmeter, that is N minus 1 into G. N we have got 20 minus 1, that is 19 into galvanometer resistance is 0.1, so it will be 1.9 ohm. Okay. Now let's see what is the relation between figure of merit K and current sensitivity capital S with the suffix I. Now see, current sensitivity is actually deflection for unit current, and figure of merit is current for unit deflection. Okay, so figure of merit is the reciprocal of current sensitivity. Okay, so current sensitivity is the reciprocal of figure of merit. Okay, K raised to minus 1. Now, 1 microammeter has a resistance of 100 ohm and a full scale range of 50 microampere. It can be used as a voltmeter or as a higher range ammeter provided a resistance is added to it. Pick the correct range and resistance combinations. See, the full scale deflection current, it's given 50 microampere. In the first case, we need an ammeter capable of measuring 5 milliampere. So the current capacity is to be increased. See, 50 microampere, and see this 5 milliampere means this is actually 5000 microampere. Okay, so from 50 microampere we have to increase the capacity to 5000 microampere. So the factor by which its current capacity is to be increased, N equal to I by Ig, 5000 by 50, that is 100. So the resistance to be connected in parallel, that is 100 divided by 100 minus 1, approximately 1 ohm, but here it is given that 2 ohm. So that statement is not true. Okay, now 10 milliampere means it's actually 10,000 microampere. Okay, so this is 200, and the resistance to be connected in parallel will be approximately 100 by 200, that is 0.5, but it's given that 1 ohm. That's also not true. And in the third case, see the voltage to be measured by the voltmeter, that is 10 volt. Now the voltage capacity or the full scale deflection voltage of the given galvanometer is actually 100 into 50 means 5000 microvolt, or say 5 millivolt. That 5 millivolt is to be converted into or increased to 10 volt. So the factor will be 10,000 millivolt by 5 millivolt, that is 2000. Okay, so the high resistance that is to be connected in series, that will be 2000 minus 1 into 100. Okay, 2000 minus 1 means approximately 2000 into 100 or 200 into 1000 or 200 kilo ohm. So this is true. Okay, see this is actually 2000 into 100, or we can say 200 into thousands, 200 kilo ohm. So that is the correct option. Okay, see, to convert it into a voltmeter capable of measuring 10 volt, we have to connect see 200 kilo ohm. So it's a range. If we want to increase the range to 50 volt, we will have to connect see 200 into 5. Okay, that will be 1000 kilo ohm means 1 mega ohm, but it's given 10 kilo ohm. So that's not correct. Okay, current sensitivity of a moving coil galvanometer is 5 division per milliampere, and its voltage sensitivity is 20 division per volt. See the current sensitivity is 5 division numerator per milliampere, and in the denominator 20 division per volt will go to the numerator. Okay, division will get cancelled. So galvanometer resistance will be 5 volt divided by 20 milliampere. See, this milliampere means 20 into 10 raised to minus 3. When this 10 raised to minus 3 is taken to the numerator, it will be 5000 over 20. That will be equal to 250 ohm. This one. Okay. Now let's see. To know the resistance or resistance G of a galvanometer by half deflection method, a battery of EMF V with a suffix E and resistance capital R is used to deflect the galvanometer by angle theta. If a shunt of resistance capital S is needed to get half deflection, then G, R and S are related by the equation. Okay, see, initially the galvanometer reading will be, okay, galvanometer reading will be this much, okay, this much. This is the initial galvanometer reading. Means the total voltage is V and the current will be VE by R plus G, because R and G is the galvanometer resistance, they are connected in series. So the current through the galvanometer will be VE by R plus G. Voltage across the galvanometer will be current through it into resistance of the galvanometer, that is G. So VE by R plus G is the current into G, that is the voltage. So that is the reading of the galvanometer now. Now a shunt is connected in parallel with the galvanometer. Okay, now see, this G is to be replaced by the parallel combination of G and S. So I have written V, then G is to be replaced by the parallel combination of G and S, means GS by G plus S. And in the denominator also G is to be replaced by parallel combination of G and S, GS by G plus S. Okay, in the denominator we will get G plus S into R plus GS, G plus S into R plus GS whole divided by G plus S. In the numerator also there will be GS by G plus S. So G plus S here and here will get cancelled. So this will be the final expression. And that voltage must be the half of the voltage initially read by the galvanometer. Okay. So this is the initial reading and half of that will be the reading when after connecting the shunt. Okay. Now this is the case. Here we have this VE and G on both sides, that can be cancelled. Okay, VE and G, and see here we will get see this 2 can be taken here. So this 2 into 2R plus G into S, that is here. So here we have 2R plus G, S will be remaining. This VEG and VEG can be cancelled. Okay, so 2R plus G into S, and on the right side there will be R into G plus S plus GS. Okay, now if you simplify this, you will get S into R plus G equal to RG. S into R plus G equal to RG. Okay, now let's see what we have next. Now focal length of convex mirror, concave mirror and convex lens using parallax methods. Which of the following statements is false? The bench correction is always equal to negative of bench error. That itself is wrong. Larger distance between two objects, larger the magnitude of parallax. Parallax disappear if the positions of the two objects coincide. Parallax can occur between any two objects. So the only wrong statement is the first one. Okay. Now the focal length of a convex mirror is obtained by using a convex lens. The following observations are recorded during the experiments. Now see, this is a ray of light incident normally on the mirror. Normally means it is incident radially on the mirror. So after reflection it will retrace its path. So this distance must be equal to the radius, or it is the radius of curvature. Okay, this distance. Now see the position of this pole of the mirror is 63.3 and the position of the image is 93.8. So the distance of the image from the pole of the mirror, that is equal to the radius of curvature, that will be 93.8 minus 63.3, and there is a bench error of 0.1 centimeter that is to be added. Okay, so we will get this is 30.6 centimeter and the focal length is half of it. That will be 15.3 centimeter. 15.3 centimeter, this one. Now a student gets a graph U versus V for a mirror. Point plotted above the point P on the curve are values of V. See, V greater than 2F. See here, V will be greater than 2F. Okay, and U will be less than 2F. And on this side, U will be more than 2F and V will be less than 2F. Okay, so here values of V will be more than or larger than 2F. Okay, now in an optics experiment with the position of the object fixed, a student varies the position of a convex lens, and for each position the screen is suggested to get a clear image of the object. A graph between the object distance U and the image distance V from the lens is plotted using the same scale for the two axes. Okay, a straight line passing through the origin and making an angle of 45 degree. See, means all points on this line will be having the same value for x and y coordinates. Okay, 45 degree with the x-axis meets the experimental curve at P. Means at this point U and V will be equal. U and V will be equal. Okay, the coordinates of P will be, see, this is 1 by V minus 1 by U equal to 1 by F, a thin lens formula. See, in this case, U is negative, V is positive. So 1 by V minus 1 by U. Okay, then 1 by F. Okay, and U will, suppose if U and V are equal, each will be equal to 2F. So this point, see, the coordinates are 2F and 2F, this one. Okay. A plano convex lens of unknown material and unknown focal length is given. With the help of a spherometer, we can measure the focal length of the lens is not possible, but we can measure the radius of curvature of the curved surface. Okay. Now, in the figure shown, the image of a real object is formed at point capital I. Okay. AB is the principal axis of the mirror. See, here the optical element is a mirror and the image formed is real. See, there are two types of mirrors, convex and concave, but only a concave mirror can form a real image. So as they have mentioned that the image is real, so the mirror must be concave. Okay, mirror must be concave. And this is the image, height of the image, that is D2, is greater than the height of the object. Means we have got a magnified image. Children, if the image is magnified, then the image distance will be more than the object distance. If the image is diminished, then the image distance will be smaller. Okay, but it's given that height of the image is real, of course it will be inverted, and it is also given that the height of the image is more than the height of the object. So the image distance must be more than the object distance from the mirror. So mirror must be like this, right? Okay, mirror must be like this. Okay, so this much is the object distance and image distance is more. Okay, so concave and placed to the right of I, that's wrong. Concave plus placed to the left of I. Okay, that's fine, that's fine, that's fine. Okay, this one. Concave and placed to the left of I. Right. Select a graph between V and U for a concave mirror. Okay, this is the UV graph. Okay, this one. Now in the displacement method, a convex lens is placed in between an object and a screen. Okay, if the magnification in the two positions are M1 and M2, M1 greater than M2, the distance between the two positions of the lens X, the focal length of the lens is. Now see the minimum distance between an object and its real image formed by a convex lens is 4f. When object is placed at 2f on one side of the lens, image will be formed at 2f on the other side. This is the case where the distance between object and its real image is minimum. Now see, suppose we have fixed an object and a screen, say at a distance that should be greater than 4f, 4 times the focal length of the lens that we are going to use. Now a lens is kept between this fixed screen and the object. If the lens is slowly moved from the object towards the screen, see, we will get two well-defined, clear, sharp images for two positions of the lens in between the object and the screen. One of the images will be magnified and the other will be diminished. See, in these two positions, object and image distances will be interchanged. Means the object distance in one case will be equal to the image distance in the other. Okay, image distance in the first case will be equal to the object distance in the other. Okay, in the second case. Now see, capital D is the distance between the object and the screen, and X is the distance or separation between the two positions of the lens. Okay, then the expression for the focal length, that is capital D square minus X square divided by 4 capital D. And see, the magnification of the magnified image is D plus X by D minus X. Magnification of the diminished image will be D minus X by D plus X. Or let us say the product of the magnifications in the two cases will be equal to 1. Okay, M1 into M2 equal to 1, or M2 is the reciprocal of M1. Now if you find M1 minus M2, you will get 4dx divided by D square minus X square. Okay, now see, D square minus X square by 4d is F. So 4d by D square minus X square will be 1 by F. Okay, so this one 4d, this one 4d divided by D square minus X square, that is equal to 1 by F. So we can write X by F. Okay, that is M1 minus M2. So F will be X by M1 minus M2. This is the expression for the focal length. Okay, now in a converging lens of focal length F and the distance between real object and its real image is 4f, means that is the minimum distance between an object and its real image formed by a convex lens, and that is the case when object is placed at 2f on one side, image will be formed at 2f on the other sides. Okay, now see, this is the case. Here the object is at 2f. Okay, when object is moved like this towards the lens, then object will come to a position between f and 2f. Then the image will go to a position beyond 2f. That image will be magnified. Okay, so when x1 is moved towards the lens, the position of the object will be between f and 2f. So image will go beyond 2f and x2 will be more than x1, or let us say x1 smaller than x2. Okay, now see, this y1 object is moved see away from the lens, means it will go to a position beyond 2f. Then the image will be between f and 2f. So image distance is smaller than object distance. So image will be diminished. Image will be diminished. Okay, so this distance y2 will be smaller than y1. Okay, will be smaller than y1. So, or let us say y1 greater than y2. So x1 less than x2, y1 greater than y2 means this must be the correct choice. What do you mean by the term parallax? When a reflected ray from the mirror are parallel, lateral shift between image of an object viewed from two different positions, that's the parallax. Okay. Now for practical use, which color we take for refractive index of a material of lens and glass? That is the mean ray. See, VIBGYOR, this is the visible spectrum, VIBGYOR. Okay, in the low wavelength region, usually we do not observe this violet and indigo because it consists of harmful radiations. So in the lower wavelength we will choose this blue, and in the higher wavelength we choose red. So the mean ray will be yellow. Okay, yellow, that is okay, this one. So yellow color will be taken for the refractive index of material of a lens, right? Now an object is placed 25 centimeter from the surface of a convex mirror, and a plane mirror is set so that the image formed by the two mirrors lie adjacent to each other in the same plane without parallax. Means image formed by both the mirrors are at the same position. Okay, image formed by a convex mirror will be behind it. Image formed by a plane mirror will be behind it. Okay, the images formed by both the mirrors are at the same position. Okay, so here is the object, it is in front of both the mirrors, and here is the image, it is behind both the mirrors, it should be. Okay, now let's see the plane mirror is placed 20 centimeter from the object. What is the radius of curvature of the convex mirror? Now see, from the plane mirror to the object the distance is 20 centimeter. From the spherical mirror to the object it is 25 centimeter. So the separation between the two mirrors is 5 centimeter. Now see, for a plane mirror the image is formed as far behind the mirror as the object is in front of it. See, or let us say the object and image in case of a plane mirror will be equidistant on either side of the plane mirror. Okay, here the object is 20 centimeter in front of the plane mirror, so the image will be 20 centimeter behind the plane mirror. Okay, now see this separation, see, from the plane mirror to the image the distance is 20. Okay, of which this much is 5. See, this much is 5, so the remaining will be 15. Okay, see, this much is 5, so the remaining will be 15. Now consider the convex mirror. Its object distance is 25 centimeter. Here is the image formed by the plane mirror. At the same location, convex mirror also forms its image. So what's the image distance of the convex mirror? It is 15. Okay, it is 15. So object distance is minus 25 and image distance is plus 15 for the convex mirror. So its focal length we can find 1 by f equal to 1 by u plus 1 by v. We will get 2 by 75. And the radius of curvature r equal to 2f, and it is 75 centimeter. Okay. Now the plot of the angle of deviation versus angle of prism for a triangular prism. Now see, in an experiment for a small angled prism, angle of prism is capital A, the angle of minimum deviation. See, this is small letter delta. Okay, this is small letter delta and this is capital letter delta. Okay, and deviation is represented by small delta. Okay, angle of prism is capital A, varies with the refractive index of the prism. See, for a small angled prism, the deviation is given by mu minus 1 into capital A. Or see, deviation, that is the quantity plotted along the y-axis. So in order to identify the shape of the graph, you have to replace the quantity plotted along the y-axis by y. So this delta, this is equal to y. Okay. And this what is this capital A? That is the angle of the prism. Mu is the quantity plotted. See, mu is the quantity plotted along the x-axis. Okay, so this is a constant, then x minus a, right? Minus a. Now see, this is the equation of a straight line, and its slope represents capital A. Okay, slope represents capital A. Now, right. Okay, and now see, point P, see, corresponds to, point P means where the deviation y coordinate is 0. Y coordinate is 0. See, when y equal to 0, we will get x equal to 1 or refractive index. See, when delta equal to 0, mu will be equal to 1. Okay, so this statement is perfect. Okay, that is true, right? Now let's see the next. A parallel beam of light is incident on a prism as shown in figure such that the rays get reflected from opposite faces. The angle of deviation delta between the reflected rays from faces AB and AC. Children, see, this is vertical, okay, vertical. Now, see, this surface makes an angle alpha with vertical, okay, and this surface makes an angle beta with vertical. So the angle of the prism is actually alpha plus beta. Okay, A is alpha plus beta, angle of the prism. Okay, now see this ray, this is vertical and it gets reflected like this. Okay, now consider, see this triangle. Okay, this triangle you consider, this triangle. Okay, now see this is the see, this is vertical and this surface, this angle is alpha. Okay, now see the same surface, similar vertical. Okay, so this angle also will be alpha. Okay, now see this angle and this angle are opposite angles, so they must be equal. Okay, right? So if this is alpha, then this also will be alpha. Okay, now in this triangle, exterior angle is equal to sum of two remote interior angles. Okay, see this is exterior angle of the triangle of this triangle, so that must be equal to sum of two remote interior angles, means this alpha and this alpha. Okay, so this we will get 2 alpha. Similarly on this side, this will be 2 beta. Okay, now see, this is the angle between two reflected rays and it is equal to 2 alpha plus beta. Actually alpha plus beta is capital A, so 2 into alpha plus beta will be 2A. Okay, so this must be the correct option. A given ray of light suffers minimum deviation in an equilateral prism capital P. If refractive index increases slightly, then the ray will suffer. See, this is the expression for refractive index when mu increases. Sin A by 2 remains constant. When mu increases, sin A plus D by 2 increases. So A plus D by 2 has to increase. See, capital A remains constant, then D has to increase. Okay, so greater deviation. Now when a ray of light is refracted by a prism such that the angle of deviation is minimum, then the angle of emergence is equal to the angle of incidence. Angle of emergence is equal to the angle of incidence. Now the graph between the angle of deviation delta and the angle of incidence I for a triangular prism is represented by, see, as the angle of incidence increases, angle of deviation decreases, reaches a minimum value and then increases. Okay, angle of deviation decreases, reaches a minimum value and then increases. Okay, now from the graph between delta deviation and the angle of incidence I, okay, then see I1 plus I2 equal to capital A plus D, where D is the deviation, A is the angle of the prism, I1 and I2 are the angles of incidence. Okay, now here it is given that this is the I1 and this 58 is I2, this is the corresponding deviation 50, right? So 38 plus 58, that is equal to angle of prism plus 50. So angle of prism we will get 46 degree. Okay, this one, right? Now see, a ray is passing through a broken prism, find the angular deviation for the ray. Now see, here see, consider this triangle. Here we have a 30 degree angle, this is a 60 degree angle. Okay, now if we complete this like this, okay, then this angle should be 90 degree, because the sum of the three angles of a triangle should be 180. Okay, now sum of these two angles 60 and 30, that is 90. So here it must be, see, so here it must be, see, this must be 90 degree, right? 90 degree. So the angle of the prism is 90 degree. Okay, and I1 is given as 45, I2 is given as 60, so I1 plus I2 equal to A plus D. A we have got 90 degrees, so deviation will be 15 degree. Okay, this one, right? Now a light ray passing through prism is parallel to the base. Refractive index of the material of the prism is. See, when the refracted ray through the prism is parallel to its base, it is in minimum deviation position. Okay, when the prism is in minimum deviation position, we can say this angle of refraction equal to A by 2. And A angle of prism will be 90 degree here. See, this is 45. Okay, so it must be 90 degree. And see, angle of incidence is given as 60 degree. So the refractive index will be sin 60. A 90 means angle of refraction will be 45. So sin 45. Sin 60 is root 3 by 2 and sin 45 is 1 by root 2. So it will be root of 3 by 2. Root of 3 by 2. This must be the correct option. Now, refractive index of a glass slab using a traveling microscope. Okay. Now see, to measure the height of water level, a student sees the pointer tip through the traveling microscope. He must have seen. See, an inverted image of the see pointer tip will be visible through the traveling microscope. So this must be the image. Now an experiment is performed to find the refractive index of glass using traveling microscope. In this experiment, distances are measured. A standard laboratory scale, a meter scale provided on microscope, a screw gauge provided on the microscope, a vernier scale provided on the microscope. Okay. Next, a mark on a tabletop is seen by a student through a microscope at a distance of 30 cm from the microscope. Seeing along same vertical path, he puts a slab in between microscope and tabletop at any position. He finds that he has to move the microscope by 5 cm away from the slab to see the focused image of the same mark. Means that 5 cm is the shift. Okay, we have a formula for shift, that is d, actual thickness of the slab, into 1 minus 1 by mu. Okay, this is shift is 5 cm and refractive index is 3 by 2. So 1 by mu means 2 by 3. So we will get d, thickness is equal to 3 into 5, that is 15 cm. Okay, this must be the correct option. A student in an experiment gets following observations: reading for the bottom of an empty beaker. Okay, it's given reading for the bottom of the beaker when partially filled with the liquid. Okay, reading for the liquid surface. Okay, so this and this difference, that we will see the difference of these two will give the actual depth, means 13.895 minus 12.324, that is the actual depth. Okay, now this 13.895 minus 12.802, that gives the apparent depth, and refractive index will be real depth by apparent depth. So we will get 1.437. Okay. Now in an experiment, microscope is focused on a scratch on the bottom of a beaker. Turpentine oil is poured into the beaker to a depth of 4 cm, and it's found necessary to raise the microscope through a vertical distance of 1.28 cm, that is the shift. Okay. The refractive index of the turpentine oil would be, see, shift is given, okay, and actual depth is also given. So we have refractive index equal to d, actual depth divided by depth minus shift. Okay, shift is given as 1.28 and depth is 4 cm. Okay, so the refractive index is 50 by 34, 25 by 7, that is equal to 1.47. Okay, 1.47, this one. Now a microscope is focused on a mark on a piece of paper, and then a slab of glass of thickness 3 cm and refractive index 1.5 is placed over the mark. Then mark will be shifted upwards. Okay, and that shift is equal to d into 1 minus 1 by mu, and mu is 3 by 2, 1 by mu will be 2 by 3, 1 minus 2 by 3 will be 1 by 3. So into actual thickness 3, that is equal to 1 cm. So he will have to raise the microscope by 1 centimeter or 1 centimeter upwards, right? Now, what is the cause of normal shift? That is normal shift, that is refraction of light. Okay. Now, on what factors apparent depth depends? Thickness of the medium, of course, nature of the medium, means it depends on refractive index, and color of light, fine, on all of these. Now, characteristics of a PN junction diode in forward and reverse bias. See, the VI characteristics of a PN junction diode is plotted as shown in figure. From the plot we can conclude that what we can conclude, see here up to this point, see the slope is very small, so conductance is very small, or we can say the resistance is very high, and here also conductance is very small and we can say the resistance is very high. The forward bias resistance of diode is very high, almost infinity for small values of V, and after a certain value it becomes very low. That is correct. The reverse bias resistance of diode is very high in the beginning up to breakdown voltage. That is also correct. Both forward and reverse bias resistances are same for all voltages. That is wrong. Both 1 and 2 are correct, will be fine. Okay. Now, a 2-volt battery is connected across AB as shown in figure. The value of the current supplied by the battery when in one case battery's positive terminal is connected to A. See, when positive terminal is connected to A and negative terminal to B, children, see, current will be coming out of the positive pole. And a diode can conduct an electric current only along the direction of the arrow in the diode symbol. See here, this is the arrow, see this is the arrow, this is the arrow. A diode can conduct electricity only along the arrow, okay, not against the arrow. So if we connect a positive pole here, current will be coming like this. That current cannot go like this against the arrow through the diode. So the current will be like this. Okay, so D1 will be forward biased or in the conducting mode. D2 will be reverse biased, and there won't be any current through this branch. So this 10 ohm resistance won't come in the circuit. Okay, so we have only 5 ohm resistance in the circuit. The cell connected, that is 2 volt. Okay, so the current will be 2 by 5, that is equal to 0.4 ampere. Now when the cell is connected the other way, means positive pole to this point, so there won't be current through this branch, so this 5 ohm resistance won't come in the circuit. See, current will be like this. D2 will be forward biased and D1 will be reverse biased. See, D1 reverse biased, D2 forward biased. Okay, there will be 10 ohm resistance in the circuit, current will be 2 by 10, 0.2 ampere. So 0.4 ampere in the first case and 0.2 ampere in the second case. Pick out the incorrect statement. The reverse current in an ideal PN junction diode can be minimum and constant before breakdown voltage. That's fine. Remains constant even after the breakdown voltage. That's false. Becomes infinity at breakdown. We have to identify the incorrect statement, this one. Okay, becomes infinite at breakdown, reverse current is controlled by external resistance. Only one statement is wrong, that is the second statement. Now, IV characteristics for LED. See, this is the IV characteristics for LED. Okay. Now, see the forward biased diode connections. There must be higher potential on P side and lower potential on N side. See here we have equal potentials on both sides, so it's not biased at all. Okay, here we have 2 volt on P side but a higher potential on N side, so this is reverse biased. Here also higher potential on N side, reverse biased. Here we have higher potential on P side, lower potential on N side, so this is forward biased, this one. Okay, the only diode that is forward biased. Identify the semiconductor devices whose characteristics are given below. See the first, this one is a simple semiconductor diode, okay, and this is a Zener diode, and this is a solar cell, and this is a photodiode. Okay, So Zener diode no, and simple diode, that is fine. Okay, Zener diode is fine, solar cell is okay, photodiode, so must be the second. Okay, now see the reading of the ammeter for a silicon diode in the given circuit. Silicon diode means the cut-in voltage, that will be 0.7. So 3 volt, 0.7 will be dropped across the diode. So the remaining 2.3 will come across the 200 ohm resistance. Okay, so 3 minus 0.7, that is the voltage across 200 ohm resistance. So the current through the circuit will be 3 minus 0.7 divided by 200, that is 11.5 milliampere. Okay, now germanium and silicon diodes start conducting at 0.3 volt and 0.7 volt respectively. In the following figure, if germanium diode connections are reversed, see there will be 0.3 volt. Now see, when this voltage is applied, this germanium diode will start conducting at a lower voltage. Okay, means 0.3 volt. So this will be conducting initially. Okay, germanium alone. And if this germanium is reversed, this will get reverse biased and this will get forward biased. So this will start conducting only at 0.7 volt. Okay, so when germanium was in conducting mode, the voltage across the load resistor will be 12 minus 0.3. When the germanium is reversed and it is in reverse biased mode, this will be conducting. So the voltage across diode will be 0.7 and voltage across the load resistance will be 12 minus 0.7. Okay, so first voltage across the load resistance 11.7, and in the second case voltage across the load resistance, that is 11.3. Difference will be 0.4 volt. Okay, this one. Now the circuit shown below contains two ideal diodes with a forward resistance of 50 ohm. If the battery voltage is 6 volt, the current through 100 ohm resistance will be. See, this is reverse biased and it will be in the non-conducting mode. Only this will be conducting. The resistance of this one is 50 ohm and here it is, here we have 150. Okay, 50 plus 150, that is 200 plus 100, that is 300. Current will be circulated like this. Okay, and the current will be 6 volt divided by 300, that is equal to 0.02 ampere. So this must be the correct option. Okay, now see, in a semiconductor diode, P side is earthed and N side is put at a potential of minus 2 volt. So we have higher potential on P side. It is forward biased or conducting mode. Okay, so it will conduct. Now see, find the equivalent resistance of the network shown in figure between the points A and B when VA greater than VB. When VA greater than VB, this will be forward biased. So we will have two resistances in parallel. This forward biased means it will be just like a conducting wire. So we have two resistances in parallel, 12 into 4, 48 divided by 12 plus 4, 16. That is 3 ohm. Okay, so 3 ohm in the first case. Okay, and when VA less than VB, so this will be reverse biased and non-conducting mode. So this won't come in the circuit. So the only resistance in the circuit will be 12 ohm. So in the two cases, 3 ohm and 12 ohm. Okay, this must be the correct option. Right? Next, which one is the correct experimental circuit diagram to draw VI characteristic curve for a forward biased PN junction? Now see, here negative pole of the cell is connected to P side. So this is reverse biased, can't be used. Okay, here see, positive pole is connected to N side and negative pole to P side. Again, it is also reverse biased, can't be used. Okay, and here we have positive connected to the P side. Okay, and negative connected to the N side. It is forward biased, but we have to measure the voltage across the diode and the current through the diodes. But here the voltmeter is connected across the series combination of diode and resistance. So this won't be reading the voltage across the diode. So this also cannot be used. Then this must be perfect. Okay, here positive pole is connected to P side and negative pole to the N side. Of course, it is forward biased. And voltmeter is connected only across the diode, so it will measure the required voltage. and ammeter reads the current through the diode. Okay, so this must be the right circuit. Now, which may be the correct possible value of reverse saturation current in a PN junction diode is of the order of microamperes. Okay, so it must be 1 microampere. Which one is the correct statement? Diode and resistor both are ohmic. That's wrong. Diode is non-ohmic. Diode is non-ohmic, but a resistor is an ohmic electrical component, and resistor flows current in one direction. No, resistor can pass current in both directions. A diode and resistor both are non-ohmic. That's false. Diode is non-ohmic, but resistance is ohmic electrical component. Diode passes current in one direction. Perfect. Okay, that's the only right statement. What occurs after a breakdown arises in a real PN junction diode when too much reverse bias voltage is applied across it? Okay, diode gets burned out. Okay, now see, during the experiment of forward bias, the least count of voltmeter is 0.5 volt and least count of milliammeter is 0.2 milliampere. If the reading of voltmeter and ammeter are 4 and 40. 4 means the each division will be 0.5, so the voltage will be 2 volt, and 0.2 milliampere into 40, that is 8. Okay, so 8 milliampere and 2 volt, 2 volt 8 milliampere, this one. Okay, now which one is the correct circuit diagram to draw VI curve for reverse bias PN junction diodes? Okay, here it is reverse biased, fine. Okay, voltmeter will read the voltage across the diode, and ammeter will read the current through the diode, and we have a microammeter, everything fine. Okay, and here it is forward biased, cannot be used to plot the reverse characteristics. Here again, this is also forward biased, can't be used. This is also forward biased. Okay, now, and here see, this is forward. Not only this is forward biased, this voltmeter will read the voltage across resistor and diode. Actually, we have to get the voltage across the diode alone. And here again, voltmeter will read the voltage across a resistor and diode. Okay, and what is the problem here? Here, see, here this ammeter is connected in parallel to the diode. Voltmeter is connected in series. Okay, this is not the right way to connect the voltmeter and ammeter. Voltmeter should be connected here and ammeter here. Okay. Now let's see, the voltage at which forward bias current increases rapidly is called cut-in voltage. Cut-in voltage. Okay. Now see, for the given IV characteristics of a PN junction diode as shown, what is the dynamic resistance of junction diode when 2 volt forward voltage is applied? Current we have in milliampere, and see, when voltage is increased from 2 to 2.2, current increases from 5 to 10 milliampere. So dynamic resistance delta, we change in voltage by change in current. 0.2 divided by 5 into 10 raised minus 3. Okay, that will be 200 by 5, that is equal to 40 ohm. Okay, this must be the correct answer. Now characteristic curves of a Zener diode and finding the reverse breakdown voltage. Now first, the breakdown in a reverse biased PN junction diode is more likely to occur due to large velocity of the minority charge carriers if the doping concentration is small. That's correct. The large velocity of minority charge carriers if the doping concentration is large, that's wrong. Strong electric field in depletion region if the doping concentration is small, again wrong. Strong electric field in the depletion region if the doping concentration is large, that's true. Okay, so the first and fourth statement must be true. So this one, right? Now, Zener diode is a PN junction which has PN heavily doped, NN lightly doped, that's wrong. NN heavily doped and PN lightly doped, again wrong. Both P and NNs heavily doped, that's true. Okay. Now Zener diode has both P and NNs heavily doped, so that it has small thickness of depletion region, that's fine. It has large thickness of depletion region due to large recombination. It has a large reverse voltage. It's weak. It has weak electric field. Only the first statement is true. Okay. Most important use of Zener diode has to have constant voltage across applied load. Okay, that's true. Any desired current at constant voltage, a PN junction working under constant regulated voltage condition, a PN junction to operate high voltages, constant voltage across the applied loads. Now in the given figure, when input voltage increases, when input voltage increases, current through RS will increase, current through IZ will increase, or the current through Zener diode will increase. But the current through load resistor will remain constant. Current through RS, RL and Zener increases, that is wrong statement. Current through RS increases, fine. Zener increases, fine, but through RL remains constant. That is the correct option. Current through load resistance won't change. Okay. Now a Zener diode is connected to a battery and a load resistance as shown. The current I, IZ and IL are respectively. Total voltage applied is 60 volt. Voltage across this branch, that is 10 volt. Okay, so the voltage here will be 50 volt. So the current through this one, I equal to 50 divided by 4 kilo ohm means 12.5 ampere. Okay, so 12.5. And current through load resistor, here we have 10 volt across 2 kilo ohm. So the current will be 10 by 2, 5 milliampere. Okay, so this is 12.5. Then IZ equal to 12.5 minus 5. Okay, this is 12.5. Current through this branch is 5. So this will be 7.5 milliampere. So 12.5, 7.5, 5. 12.5, 7.5 and 5 milliampere. Okay. Now, which of the following statements is correct for proper working of Zener diode? Reverse bias voltage should be less than or equal to the breakdown voltage. That's wrong. Reverse bias voltage applied must be greater than Zener breakdown voltage. That's fine. Zener is to be forward biased. That's wrong. Okay, for a given Zener diode, there can be different Zener breakdown voltages. That's also wrong. Only the second statement is correct. Okay, for the circuit shown below, the current through the Zener diode is, see here we have 120 volt. Okay, and 120 volt, this is 50 volt. So current through this will be 10 kilo ohm. See, current through 10 kilo ohm will be, the voltage across 10 kilo ohm is 50 volt. So 50 divided by 10 means 5 milliampere. IL equal to 5 milliampere. Total is 120. The voltage across this is 50. So here it will be 70. 70 volt by 5 kilo ohm, that is 14 milliampere. So 14 milliampere will be coming like this. 5 milliampere will be going. So IZ will be 9 milliampere. Okay, IZ equal to 9 milliampere. Right? Now see, in the given circuit, the current through Zener diode will be, see here we have R2 and here also R2, 1500 in parallel with another 1500. So the voltage between, resistance between these 2 points will be 750. Okay, here we have 500. Okay, and across these 2 points 750. So the total voltage will be dropped in the ratio 2:3. Okay. 2:3 means 12 volt is to be divided into 2 plus 3, 5 equal parts, in which 2 parts across this one, that is 4.8, and 3 parts here, that is 7.2. Okay, so the voltage across the diode will be 7.2, that is smaller than the Zener voltage. Okay, so the current through the Zener diode will be almost zero. Okay. Now because see, it will conduct, or there will be a reverse current only when the voltage across this is 10 volt, but here the voltage is only 7.2. right? Now see, figure shows a DC voltage regulator circuit with a Zener diode of breakdown voltage 6 volt. If the unregulated input voltage varies between 10 volt to 16 volt, then what is the maximum Zener current? See, maximum Zener current will occur when the input voltage is maximum, that is 16 volt, in which the voltage across Zener diode is 6 volt. So the voltage here will be 10, and the current through this will be 10 by 2 means 5 milliampere. Okay, current through this will be, what is the maximum Zener current? Current through this will be 5 milliampere. Okay, here we have, see, this is 10. Okay, this is 5 milliampere. Here we have 6 volt. Okay, divided by 4 kilo ohm means 1.5 milliampere. See, 5 milliampere will be coming, 1.5 will be going like this. So the current through this will be 3.5. Okay, 3.5 milliampere. This one, right? Okay, this one 3.5 milliampere. Now, Zener breakdown occurs when a PN junction having P and N lightly doped, no heavily doped, and have narrow depletion layer. Okay, that is the characteristics of a Zener diode. Now, the reading of ammeter in the following circuit. See, when a Zener diode is forward biased, it will be just like a silicon diode. Okay, so when a voltage is applied like this, this is a forward biased Zener diode. So it will act just like a conducting wire. Okay, and this is reverse biased. So the voltage across this will be 15 volt, and the remaining voltage will be across 10 kilo ohm. So the voltage across 10 kilo ohm is 5 volt. So the current through the circuit will be 5 divided by 10 kilo ohm, that is 0.5 milliampere. Okay, this one 0.5 milliampere. Now, in the incorrect statement about the property of a Zener diode, Zener voltage remains constant at breakdown. That's correct. It is designed to operate under reverse bias. Fine. Depletion region formed is very wide. No, it is very thin. Okay. Next, which diode is designed to work under breakdown region? That is Zener diode. Okay. Now see the actual symbol of Zener diode, that is this one. Okay. Now Zener is different than PN junction diode due to higher doping and higher breakdown voltage. Okay, higher doping and lower breakdown voltage, that is the correct option. Okay. Consider the following statements A and B and identify the correct answer. A Zener diode is connected in reverse bias when used as a voltage regulator. That's fine. Okay, the potential barrier of a PN junction lies between 0.1 to 0.3 volt. See, actually potential barrier for germanium is 0.3 and for silicon it is 0.7. So the second statement is wrong, first statement is true. A is correct and B is incorrect. Now, what happens during breakdown in Zener diode? Both current and voltage across Zener diode are fixed. That's wrong. Current will increase. Both current and voltage across the Zener diode are varying. That's wrong. Voltage will be fixed. Current increases rapidly, but voltage remains constant across it. Okay, that's fine. Now, see in the circuit, what is the output voltage? See, we have input voltage 120 volt. See, Zener voltage, that is 40 volt, that will appear across the load resistor 5 kilo ohm. Okay, so this must be 40 volt. Now let's see, we have a Zener diodes having Zener voltage Vz equal to 10 volt and power dissipation Pz equal to 0.4 watts. Okay, so we can find the Zener current through the Zener diode, that is power divided by voltage, that is 0.04 ampere. 0.04 ampere, that is the current through the Zener diode. Okay. Now, if the diode is in its breakdown condition, then what should be the minimum protective resistance Rp connected with it in series? Okay. See the maximum voltage, that is 15 volt. Okay. 15 volt, and the voltage across this Zener will be, that is voltage across this is 10 volt. Okay, and see the voltage across this will be 5 volt. Okay, 5 volt, and the current through the Zener diode is 0.04. Okay, so the resistance will be 5 divided by 0.04. Okay, voltage across this is 5 volt because 10 volt will be dropped here, and current through this branch is 0.04. Same current will be passing through this and Zener diode. Okay, we have got the current through Zener diode, that is the current through this protective resistor. voltage across it is 5 volt. So the current will be, see, 5 volt divided by 0.04, that is equal to 125 ohm. Okay, 125 ohm, this one. Now component identification means identification of resistor, capacitor, diode, LED, like from a mixed collection of such items. And see, for using a multimeter to identify diode from electrical components, choose the correct statement out of the following about the diode. It's a two-terminal device which conducts current in both directions. No, it's a two-terminal device which conducts current in one direction only. That's fine. Okay. Now see, a carbon resistor 47 plus or minus 4.7 kilo ohm means the tolerance, percentage tolerance, that 4.7 is actually 10% of 47. Okay. Now see, here we have the color code here. See, this 4 corresponds to yellow and 7 corresponds to violet. Okay. So yellow, violet, right? Yellow and violet. Then power is actually 10 kilo ohm means 10 raised to 3, and then orange, yellow, violet, orange, and the percentage tolerance is 10%, that is given by silver. So yellow, violet, orange and silver, color code must be like this. Okay. See, first two bands represent the first two significant digits. Third band will give you the decimal multiplier or the power of 10. Okay, here we have kilo ohm means 10 raised to 3. So the third band must represent 3 or orange. Okay, fourth band will give you the percentage tolerance. Here we have 4.7, it is 10% of 47. So it must be 10% or silver. Okay. The color code of a resistance is given by yellow, violet, that we already know, 4 and 7. Then brown stands for C1, that is 10 raised to 1. Okay. And then gold, that represents a tolerance of plus or minus 5%. So 470 plus or minus 5%. 470 ohms and 5%. Okay. Next we have orange again, that stands for, orange stands for 3. Then we have blue stands for 6. Then we have yellow stands for 4, means 10 raised to 4. So 36 into 10 raised to 4. Finally we have gold, plus or minus 5%. 36 into 10 raised to 4 means 360 kilo ohm. Okay, 360 kilo ohm. Plus or minus 5% means it is 18. So 360 plus or minus 18 kilo ohms. Okay. Now children, we have discussed all topics from experimental skills strictly according to your updated syllabus. See, you need to expect only this type of questions, or you have to learn only up to this level. Thank you.